Math machines, pig or bacon, using piecewise defined functions to model complex motions. The task is to design and test mathematical models for the motion of a car with multiple accelerations. The software is the function plane piecewise program with a setup file pig or bacon. The hardware is the function plane with a screen, meter stick, and a dry erase marker. The heart of the function plane is a high-tech servo motor 7975, and it is possible to build this device yourself directly from that motor. Uniformly accelerated motions have been well described since the time of Galileo, but real motions are often far more complex. Fortunately, even very complex motions can often be described and recreated as a sequence of separate motions, each segment with its own constant but different acceleration. The position of an object moving with uniformly accelerated motion can be written as a function of time in the form x equals x0 plus v0t plus 1/2 at squared. X is the instantaneous position, x0 is the initial position, v0 is the initial velocity, a is the acceleration, and t is the time. Although written in a different form with different symbols and in reverse order from those typically used in math classes, this equation is a quadratic and has all the mathematical properties of the function y equals ax squared plus bx plus c. The equation is only valid when the acceleration remains constant, but it can be reset and restarted to model a sequence of motions. Together, the resulting sequence of functions can provide a piecewise defined function which specifies the location of the object at any time. The task we're giving the students is somewhat like a homework problem, but it is different in the sense that it's both more dynamic, more general, and more physical. A car moving at a constant speed of 25 meters per second goes over a small hill where the driver spots a pig in the road ahead. Assume the driver immediately applies the brakes, resulting in an acceleration r1. Replicate the motion using a scale model where 1 millimeter represents 1 meter. The motion in your model should begin 200 meters before the hill and continue until the car has stopped moving. Using function plane piecewise, we're loading the activity file pig or bacon. A few things to notice. It is using x as the output, and the units for x have been set in this file to be millimeters rather than meters. We're also displaying the initial position, and that's also in millimeters. And we have one manual control, the real number r1. The program is using the default coordinate system such that the 0 position for x is at the center of the function plane, negative positions are to the left, and positive positions are to the right. This is also set up so that there are 2 piecewise segments planned, but those have not yet been completed. And that is really the student's first task, to come up with an equation to define the motion during the first segment. Before putting in the function there, we might want to put in the given information that the motion starts when the car is 200 meters from the hill, and in our scale model that would be negative 200 millimeters. Then we need a function to actually control the motion until it gets to the hill, the first segment, and a reasonable way to do that would be to say that x is equal to negative 200 plus the speed, which was given to us as being 25 meters per second or millimeters per second in our model, times t. And since this is a constant speed, there's no acceleration to add into this. There is another issue here, that the segment duration now is showing as being 0, and that can't possibly be correct. We need to know how many seconds it's going to continue to move from the negative 200 point to the hill, and since it's going 25 per second, that should mean that the total time required is going to be 8 seconds. From there, we need to think about the second segment, and the second segment, hey, the numbering does go 0, 1, even though we're talking about 2 segments, so the second segment is segment number 1. Is going to be a little bit different to define. It is going to be again in the form x0 plus v0t plus 1/2 at squared. The initial position for this is not the -200. The second segment is starting as it comes over the top of the hill, so that the x0 is 0. We don't really need to include that explicitly, but hey, we can. It doesn't hurt to put it there. Plus the initial velocity, and as it comes across the top of the hill, it is going at 25. So we have 25 times t plus 1/2 the acceleration. Let's write that as 0.5 times the acceleration, and we don't know yet what the acceleration is in this model, but it's supposed to be set by the slider above, and so we put in r1 times t squared. We don't yet have a complete answer to the task, especially we haven't dealt with the R1 issue, but it's reasonable to go ahead and do a partial run to see if we're headed on the right track. And sure enough, we've got the laser pointing at the front of the car. If we start, the laser begins its trip at a nice constant speed, and after 8 seconds it reaches the top of the hill and looks like something has gone wrong. The pig certainly didn't do very well on that trip, but I think there may in fact be a significant issue going on with our model. Now the issue in fact has to do with the definition of t, that we reset the initial value for x as we came to this, but we did not reset the initial value for t. As it began the second segment, the calculation was using the total time since the very beginning of the sequence of the total motion, and after the 8 seconds it began to plug 8 seconds into the formula and came out in the very wrong place. We needed to reset t somehow, and there are two ways that that could have been done. One of the ways would have been to note explicitly that we wanted to use the time since after the first 8 seconds, so that we could have, instead of put in t, put in t minus 8 for each one of these. And if we run it again, t works just fine during the first segment, since it is the first segment. And by using t minus 8, I think we've managed to get past the initial problem that we had. The software allows us another way to solve the same problem. If instead of using t or t minus 8, we could have used ts to be the time within the segment. And if we make that replacement in both of the cases and use ts instead of t, it will restart automatically at the beginning of each one of the segments. The next logical step in this is to deal with the issue of the actual acceleration, the r1. Some students will probably be tempted to find it by trial and error, but the pig won't appreciate that, and it is not the most efficient way. And wise teachers will also probably ask that students show their work to show that they've understood the more efficient way to find it mathematically. And the equations of uniformly accelerated motion do find an appropriate method to find the right acceleration to get it stopped. And that calculation also requires some measurements, since we've never really given the students the distance from the top of the hill to the pig. When I did the measurements with the setup here, the answer that I got was negative 0.184 for the acceleration. I could have entered it with a slider, but for a fraction it's much easier just to type it in. And if we now try that, again we have the initial constant velocity. We now have the velocity decreasing in a uniform way. Looks like it may be stopping soon. didn't quite get there, and in fact didn't quite stop moving. And the reason for that has to do with the segment duration. We made a rather wild guess that the correct value for the segment duration should be 10 seconds, and that didn't really seem to be long enough to get things stopped. If we try again and do another calculation, we may find that it actually takes about 13.6 seconds for the motion to stop. So we'll try one more time here. And I think we did really, in fact, find the time and the correct acceleration to get it stopped just before it hit the pig. Hopefully students will also recognize that this is a pretty easy acceleration unless you're on ice, and the pig is actually relatively safe. Many other modifications to this, for example, the velocity can certainly be increased from 25 to 30, 35, 40 meters per second to see what effect that might have. The pig can be placed in all kinds of random positions to see what difference that makes. And those other investigations are a very important part of this whole process.